So what we're now going to do is something really spectacular. It's a live quantum physics experiment, quantum simulation project. And it's led by our RQT fellow Alexandra Waldherr, together with fellow Franz Pfanner and quantum physics student Changxiao Sun.
Yeah, I'm Franz, and you've already heard from Alex and Daniel. We're going to tell you a little bit about quantum simulation, give you a short demonstration. Hopefully this will, help maybe uncover some of the mysteries or demystify some of the things that have been talked about. Here, a short outline, what are we going to do? What is quantum simulation? And we'll also talk a little bit about Rydberg atoms. That is just one of the platforms in the quantum world right now, but we had a cool demo that might be interesting to everyone here. And then we will show, part of this demo would be the Ising model on this pulsar Rydberg simulation. And we'll talk a little bit about classical simulation of quantum circuits. So a lot of the real quantum computing problems can't be solved yet on a quantum computer, at least to my knowledge. And then we'll end with a live photonics demo, which hopefully will get you all inspired, that everyone can learn some quantum physics to some level. So yeah, there's two aspects that we're going to talk about: investigating real world on quantum simulation experiments. So there's a lot of talk about low energy phases, molecules, but also talking about the computers. So here's some examples in the Rydberg world doing these ordered atoms where you can have structures like materials, which can hopefully lead to some questions about low temperatures or high temperature superconductors, and just generally, I'd say, very interesting questions in physics, but will also lead to industry-changing applications. On the right, you see this is from a recent publication from Michel Lueken's group at Harvard, talking about doing general quantum computing with Rydberg atoms. So here, with Rydberg atoms, the atoms themselves are the fundamental qubit, which is very interesting because they're all naturally identical. We've heard a lot about superconducting qubits or other types of qubits, which are engineered systems where we try to tune the parameters and make sure they're all really behaving as quantum systems. If we use atoms, every atom is identical and inherently has these quantum properties that we want. We can generate entanglement with this Rydberg interaction. So this was really pioneered at Harvard with Michel Lueken's group. And you can see here, this is an image from a very recent publication from my group at Caltech that shows over 6,000 atoms in one system. So when you hear about tens of qubits or hundreds of qubits, the research is really growing exponentially, and we're now talking about tens of thousands pretty soon, 6,000 from this year. And these atoms can be entangled really by going to these high energy Rydberg states. So normally atoms are at that sub-nanometer scale, very small, but with lasers we can make the atoms actually very large to microns, which is close to the size of human hair, and we can really bring these quantum properties from individual atoms to large systems, which we need for quantum computers. And then something that was very essential and kind of interesting about this platform is this arbitrary connectivity. So we can move the atoms with the laser. So this is from the Harvard's group, where you can actually see two groups of atoms. One is being moved around, and a lot of the problems with quantum computers right now that you've heard about probably is you can't actually connect a lot of the qubits or entangle them over large distances, which are major problems and things that are necessary for universal quantum computing. And every system has its upsides and downsides, but this is one of the reasons why this system is interesting, and also one of the systems we're just trying to show you today.
Okay, so we will later talk on something about pulsars. So first I will start with what is pulsar. So when we think about the quantum computer, we have different levels of abstractions where users or scientists interact. Scientists interact at a very low level of abstraction, so they interact directly with wave functions or qubits, depending on the theoretical experimental part. And pulsars like kind of some level where we can, with a computer, kind of simulate the experiments that we would like to run in the lab, or coordinate the experiments that we would like to run in the lab a little bit. And then the next abstraction level is to work with circuit diagrams. For For example, this is what IBM is doing. You can go there and you can drag and drop your gates and something like that, and then somebody else has to worry about how these gates then can be put onto an experiment. And circuit diagrams are abstract and therefore not very useful for experimentalists that have to be in the lab or for the quantum computer that really has to execute these observations then in real life. And one of the models that we will try to kind of understand with the help of Pulsar, or how Pulsar works, is the Ising model. So the Ising model is for some people in physics very familiar, and for some people who are not coming from a physics background, maybe not so much. What the Ising model means is that we have different spin particles that are sitting in a chain, and the neighbors can interact, and the neighbors often also align either in two different ways, which means they can be aligned in the same direction, which is called ferromagnetic alignment, or they can be different in the different directions with the spins, which is called an anti-ferromagnetic alignment. If you put this, for example, in external magnetic field, the external magnetic field, for example, pulls a push onto one direction, so it prefers one direction for energy. And this is a toy model that physicists really like to play around with. And this can be scaled from 1 dimension to 2 dimensions. And you can look at different temperatures and see different phase transitions. For example, here we see that this is mostly this anti-ferromagnetic ordering, where the neighbors are aligned in different directions. But then if you go to different temperatures and different settings, this could be a ferromagnetic state, where everything aligns into, for example, in the same directions, and then we get the magnetic ferromagnetic materials we know. And from the model in the magnetic sense, like in the visual sense, we can make a mathematical formula, and this is like the Hamiltonian. And the Hamiltonian is very familiar to everybody from chemistry or from physics. The Hamiltonian just generally describes the energy of a system. And every system strives to achieve minimal energy, normally. So what you see here is this coupling constant between two neighbors, so this defines the interaction between these two neighbors. It's called J. And if you see here in this formula, the two neighbors are the sigmas, which are these kind of sigma-shaped thingies here. And the energy from two neighbors, if they are aligned in the same direction, for example, +1 and +1, then they, as a product, make also a positive number. So if the coupling constant is also positive, so J is positive, and the minus is in front of the sum, the first term aligns to a negative energy, and therefore it is improving the alignment in the ferromagnetic order. If J is negative, then it provides the anti-ferromagnetic ordering. So now we go to the Ising model simulation, and here we want to create a Rydberg register, and then we want to create a pulse sequence, and then we want to analyze the result. What this means is that in the Rydberg register, we want to have this Ising model where you have neighbors interacting. Therefore, this Rydberg interaction that Franz mentioned before should only overlap for neighbors and not over the whole system, but we will see kind of effects propagating over the system. And then we will have the pulse sequence, which kind of puts in the energy, and then we can analyze the results. So Pulsar, which is this framework here, we provided a video just for time frames. You can go to the docs, and you see here that they first have this register, and you can apply energy or like the light in a global form, or you can specifically target specific atoms here. I really recommend going through all different kinds and like trying different codes. For example, here's one code that we now also kind of adapted from the anti-magnetic ordering. So the code that we wrote is you start with defining the pulse parameters, and they have here this omega, which is, and you have also this delta. And kind of you can understand the omega as the energy that is exactly needed to go from this, for example, one spin station to the other spin station. And the delta is kind of a little bit less or a little bit more than you really need. And you can see it when you define the sequence that the purple part is giving you at the beginning a little bit too little and then a little bit more, this delta. And we see here that if you will stop this briefly, a phase diagram. So this blue part here is where you get the antiferromagnetic ordering, which is a fragile one, where those are differently aligned. And we start at the bottom, then we kind of entangle the system, and then we would like to end with the detuning just a little bit above the energy that is really needed for the exact transition. We run the simulation here. We plot the histogram. And you see here which state is the one with the highest probability. Exactly the one where 1, 0, 1, 0, 1, 0, 1, 0, all of them are in antiferromagnetic order. Now if we go further and go back to where we define the detuning, which means we can be redshifted, we apply a little bit too little energy for the whole system to interact well with each other and to go from here I put 0. We create the pulse sequence again. You see the violet part is only below the 0 line. Then we run the simulation again. We are below this phase where we would like to be. We run our simulation, we run the probability results. Aha, now our qubits or our Rydberg atoms are all in the 0, 0, 0 state. And if you do it in the other way direction, sorry, so kind of started from beginning. Okay, it started from beginning. I don't want to show everything again, but if you apply too much energy, you will get the exactly other order where everything is in the 1, 1, 1 state.
All right, thanks Franz and Alex for their good explanation on how to use Rydberg atoms to simulate antiferromagnetism. I want to take a different spin on the whole quantum simulation question by showing how to simulate a quantum computer with classical methods. And let's start with how to solve any computing problem. Now, to solve any computing problem, first you should, why is it autoplaying? Spoilers. You should go to university for 4 years for your bachelor's, and maybe master's for 2 years. Industry experience, academia, takes a few decades. But when we were engaged for this talk, Mauritz told us we had 15 minutes and not a few decades. So unfortunately, we have to simplify it a little bit. In essence, you think through the problem and ideate a solution, then you take your laptop, you code it up, test it to see if it works, use those results to debug and iterate. Now, how would you do this with a quantum circuit? Do you have a quantum laptop? If you do, I'm very jealous. I do not. So you could try and, oh my gosh, you could try and run it on a real quantum computer, but this takes a lot of waiting time because there's many people want to use quantum computers, but not that much supply. The most convenient method would be to use your laptop, and this is the best option for prototyping circuits with small size. Anyone can, on their laptop, download the IBM Qiskit library and use their state vector simulator to explore quantum circuits. Essentially, how the state vector simulator works is you start with an initial state, you can apply your quantum gates, which it's important for the demo later to keep in mind that the order in which the gates are applied is important. And then at any point, you can see the intermediate state vectors, and then at the end, you can apply measurements to simulate kind of what you would get in a real experiment. Now, this raises a few questions, like what is a state vector? Well, the state vector is a mathematical description which encodes all the information about a system at any given time. A measurement collapses the wave function probabilistically, so in real life, we only see the probabilistic statistical results and not the actual state vectors themselves. So this is actually more powerful than in real life. We get all the information, we get the exact probabilities of any measurement outcome happening. And when a measurement is applied, you can see, oh my gosh, you can see each state vector then collapses to either up or down. In this case, it happened to collapse to down, down, up, but it could have been equally likely to go to, for example, down, up, down, up, etc. When you run a real experiment, you have to run it many times to aggregate these statistics of what kind of up and down you can get. Now, if this is so good, why do we still care about making quantum computers? Well, it turns out that there's important pitfalls. The state vector gets very big as your circuit gets big. The size of the state vector scales exponentially with the number of qubits in your circuit, so that we're pretty much limited to only simulating about 30 qubits because of the memory requirement. And if you double your computing power, say you buy 4 more laptops, then you can only really simulate maybe 2 more qubits, which is very bad diminishing returns. This reflects the fact that we're pretty sure that quantum algorithms are more powerful than classical algorithms, which would imply that there's no efficient simulation of quantum computers on a classical computer. And now it's the moment you've all been waiting for.
Okay, so this is the experimental part. So if you think of a quantum computer, you first have to prepare your states. And in our case, the polarization filter prepares our states. You can think of it like in the picture there. It's kind of a fence where only specific parts of light go through that polarized in certain directions. And if I put the fence that is in the end, kind of the measurement, in the exactly opposite direction, nothing goes through and we get black, right? Now there's some specific kinds of materials, specifically just the tape that you have lying around at home, like plastics, that if you put it in between there, it kind of rotates specific parts of light, which means it elliptically polarizes the light that comes through the first filter. And therefore, it means it kind of also sorts the light by interference a little bit. And if you put it here, you see that there's some light coming through. And if you flip it around, you see that there are colorful patterns, right? So kind of each tape kind of acts like a little bit like a quantum gate in between. And the filters kind of act like preparing the state and measuring the state. And the cool thing is that I prepared some tape, you know, like. So if you add more tape to it, then more colors can kind of add to it. So, and if you add even more tape, you have to be very lucky to get like the correct colors. I mean, probably somebody can calculate with how I get the coolest colors. We can do this, very nicely. Now we have a little bit of more of red and cyan added in here. And the thing is that, for example, at me at the university, we also use this in the way that we put plastics in there that are quite big models, for example, bone models. And this you can then use for stress testing. So also if you put strain on the plastics, it changes how often or like how densely they kind of polarize different colors in the light spectrum. And this autoplay at the moment is making me really, really aggressive. And so if you see here, this left on the right side, this model of the bone, you see that you can see where the the colors are most dense together in lines. This is where most of the strain is. And also in your bones, this is where the bones over their time in evolution have become most strongest with the trabecular structure to kind of put the strain load very well and get you through the day. So if you want to put tape onto the filters, we can make a kind of community collage here, and then we have it for the next conference. And also if you want to have the code fully shown, I can definitely run it for you. Just come to me and I will show you because you didn't see the end part on the video. Okay, yeah.
Thank you so much for that brilliant experiment. Next up is Jin-Hee, Katie, and myself, and we are going to give a talk about a VR project that we are currently demoing. And unfortunately, the people from VR department aren't able to be with us here today, but let's just get onto stage and present our ideas about this to you. Please join me. So imagine what if an audience like you, what if audience members could become part of the orchestra, either in real time or years later as belated guests? And what if artists could use algorithms to transform their hand and body movements into audio and abstract visual feedback to the audience during a show? This interdisciplinary research project in collaboration with the Stanford Virtual Human Interaction Lab, led by Professor Jeremy Bailenson and Brian Beams, aims to integrate spatial computing and mixed reality, interactive AI, and quantum-centric computing, and even HCI, human-computer interaction, with artistic expressions that we have witnessed here today during the musical interludes, to make both scientific and applied progress, while also addressing L-speak considerations across the market verticals. And our initiative includes having an ensemble of the Royal Concertgebouw Orchestra from Amsterdam do an entire performance on Stanford campus here, together with soloist Jin-Hee Lee and Katie Liu, playing Rossini, Chopin, Mahler 1, wearing the MR headsets. You know them from Meta and from Apple, the goggles. And today we would have hoped to showcase you a first stage experimental setup to design to capture and record their unique gestures and even emotion tracking, allowing you to connect even more with them immersively. I showed already in the previous Fractal Art demo some of the demonstrations that we had done. It's really spectacular and really difficult to perform with those. Since the VR department cannot be with us here today, Jin-Hee and Katie won't have to perform with the goggles. But we think there are use cases, and many may seem avant-garde and visionary, but the potential of quantum-empowered virtual reality is VR on steroids that revolutionizes performance and security and adds quantum centers that Lindsay talked about on the submarines for better tracking. And I think that quantum VR will bring us novel application areas in healthcare, but also in entertainment and gaming, quantum networking for multiplayer VR. We think, most importantly, that quantum can make VR safer and more ethical as it employs quantum encryption and key distribution protocols to secure virtual environments and safeguard data privacy and human rights. As a PET, as a privacy-enhancing technique, and PQC and QKD could be used to really create secure communication channels for VR applications, protecting users from eavesdropping, from hacking, and from unwanted intrusions while you are so vulnerable in VR. Let's name it quantum spatial computing or the quantum metaverse. It's a very tiny metaverse. Over to Jin-Hee and Katie for your thoughts.
Thank you, Mauritz, for having us all here today and for the chance to speak about our quantum VR project. So as a student and coming from a background of both computer science and music, I have seen and experienced firsthand how the arts and humanities and the sciences are often painted to be at odds with one another. But we here in this room, I'm sure, are well aware that incredible power can emerge when we see how these two can work together and harness the strengths of both. And I believe that our VR project is doing just that, so I look forward to continuing our research in that domain. And looking ahead, again, coming from the HCI human-powered background, I feel inspired by the RQT core mission here. And in line with the mission, my pledge would be to keep technology from straying from its very makers. And as I think about areas of future research and innovation, I'm committed to human-powered quantum for quantum-powered human advancement, right? I'm committed to keeping the humanity in all of this amidst this storm of technology that we're seeing evolve rapidly. And thus, we predict the emergence of a new field and want to emphasize its importance, quantum human-computer interaction, or QHCI. The current field of HCI and what I've been learning in classrooms all these years here and the top leading institutions of computer science, these HCI curricula teach what it knows, which is classical computing. However, the advancement of quantum computing necessitates a dedicated shift in HCI research, no longer thinking in our binary classical computing model of everything is yes or no with zeros and ones, but now moving to qubits, represented by this superposition of multiple possible states and moving beyond this binary model and binary states. As we see this paradigm shift, it also pertains to combinations of quantum tech with interactive and conversational multimodal AI, as we've touched on today as well. And this will require a novel class of quantum classical interfaces. As we can see we haven't really touched this in HCI studies and makes it all the more important to further research this field. And with quantum power being far beyond what the mainstream society may consider imaginable, it's all the more important that we make these interfaces accessible to human beings. Since we are approaching the field of QHCI early on, we have the power and the responsibility to approach it ethically, actively stewarding toward beneficial societal outcomes. Specifically, we'll be using the LSP framework that has already been established here at the RQT Center. And as we shape the future of interaction between ourselves and the machines and quantum technology, I look forward to keeping humanity at the forefront of this rapidly evolving field. So I'll turn it over to Katie to continue to talk about quantum neuroscience.
Thank you so much, Jin-Hee and Mauritz, for those wonderful words. My name is Katie Liu, and I'm a junior pursuing a dual degree in computer science and music here at Stanford, and it's such an honor to be here with you all today and to hear your amazing thoughts. Let's imagine the future classroom where quantum VR apps allowed students to play around with a world-class ensemble, experiencing firsthand the intricacies of musical expression among renowned compatriots from different instruments and conductor perspectives to interacting with sheet music in real time. However, I feel that quantum extends far beyond VR at current technology readiness levels. Riding on today's leitmotif of applying quantum to healthcare and the life sciences, I'm left with many, many questions and possible avenues of exploration I'd love to delve into. Let's imagine leveraging quantum computers and simulators to model the mechanics between neurotransmitters and synaptic transactions, leading to novel treatments for neurological disorders and targeting specific quantum level processes. Let's also imagine using lightweight quantum sensors in a wearable brain scanner to measure magnetic fields, leading to new insights into how memories are formed and stored. Fundamental links exist between quantum theory and the human body. As such, do quantum phenomena create conscious experiences? Do they fuel the investigation and treatment of irregularities in bodily functions? I spent the past few years here studying medical technology, both inside and outside of Stanford. Neuroscience, law, human rights, agency, identity, quantum, and AI, they are all intimately tied together. I'd love to leverage my experiences at the Interdisciplinary Brain Sciences Institute, Stanford HAI, and as a 2024 Curis Research Fellow to build on the RQT core mission that we've established here and work on an RQT project that studies the question of whether we should consider the brain as a quantum system, and applying the RQT framework and ELSP's legal and ethical dimensions to the life sciences industry. There are many, many thought-provoking but unsolved enigmas that await us in the quantum realm, but I'm so ready to be here with you to shape the future of brain-computer interaction and define what makes us truly human. Thank you very much.
And I'm so happy and so proud to see you become so well-versed well-versed scholars in quantum at such a young age. And therefore, I'm proud to announce that Jin-Hee and Katie, these exceptionally talented and dedicated women in quantum, will be preserved for the university and become fellows at our centers after they graduated to be lead investigators of their own RQT projects. And for Jin-Hee, this is in a couple of weeks. And for Katie, this is in a year. And in the meantime, Katie will be my research assistant at the center. And we plan ahead like a symphony orchestra. And please join your hands for their achievements. And to end this segment, Jin-Hee and Katie will treat us to musical interludes.
A non-VR music.
Yeah.
Thank you so much.
Thank you.
all'ombra mostrarsi, l'ombra Ciò